In the last video, we have introduced the Schrödinger equation as a way to treat the behavior of small particles that have quantum mechanical behavior. In this video, we try to analyze a little bit what the wave function means. Okay? One of the interpretations of the wave function was provided by Max Born, and that says that the wave function is related to the probability of finding a particle in a given region of space. As a matter of fact, the equation that we use to calculate the probability is as follows. The probability is going to be equal to the integral of the wave function squared of the particle over the region of space that we are interrogating. Okay, so let's see what this means. Suppose that you have a particle that has quantum behavior, and that particle is only moving in one dimension. Okay, so the particle can only do this type of motion, move from left to right. Okay, and let's assume that the wave function for that particle has this shape. Okay, we plot here the wave function as a function of this x distance, and this goes from 0 to a distance L. And again, x means that you're actually only moving in the x-axis. Okay, and suppose that this wave function happens to have this shape. Okay. Okay, so this wave function is symmetric, should be symmetric with respect to the middle of the box. What this interpretation is telling you is that if you take the squared of this wave function and integrate it over the region of space that you're interested in, that will be the probability of finding the particle in that region of space. Okay, so let's see how the psi squared would look like for this case. Okay, so now if we now take the squared of the wave function, and again the x-axis is the same. Okay, now this is going to look a little bit like this. Okay, it's perhaps a little exaggerated, but you get the idea. Okay, so here's the idea. We can ask the question now. Okay, can you please tell me what is the probability that the particle is in the left-hand side of the box? Okay, so we can take this region of space, which is the left-hand side of the box, and the integration of psi squared over 0 to L halves. Okay, so this, the area under this curve, that is actually going to be the probability of finding the particle in the left-hand side of the box. Of course, in this particular case, because the particle spends equal amount of time on the left-hand side of the box and the right-hand side of the box, that probability should be 0.5. Okay? And again, if we actually want to see how this would turn out to be, again, what we will do is calculate the probability from 0 to x is equal to L halves, okay, of this wave function. In this case, we don't have a volume, okay, because the particle is only moving left to right in only one dimension, and we're choosing that to simply be x. Right, so notice how, again, we'll plot psi squared versus x and integrate. That is exactly the area under the curve. Okay, and this is very useful, as you can see. Now, of course, let's try to do something a little more complicated. We knew that because this function is symmetric, you have equal probability to be to either side of the center of the box. But we can ask a much more interesting question. We can say, well, can you please tell me what is the probability of finding the particle in this region right around the center? Okay, that is the region of maximum probability. So again, if you now integrate this from this point x1 to x2, from x1 to x2, okay, that will be the area under this curve, and that is exactly the likelihood, the probability that the particle will be found in that region of space.